Good afternoon, everyone. Uh, Thank you so much for staying here. And then this is Trinadha from and I'm from IIT Hyderabad, India. And this is my colleague research. I'm going to present here. Yeah. Here is the title of the Porous Silk Scaffold-Integrated TENG for Sustainable Energy and Harvesting. And the outline of the presentation, initially I'll try to discuss about the motivation of the in this work, and then after that what is the introduction of TENG, and then after that how to fabricate the TENG, and then working principle of TENG, and then I'll also discuss the resultant discussion, and then followed by I'll also discuss the where we can use this kind of a TENG device, and where we can get the more power. Okay. And as you can see here, as you can see from graph, most of the IoT devices, most of the people are using conventional battery, which are having these are the challenges. The problem is you need to every time you need to change the device, and you need to maintain the device, and the disposable also problem. And then it most of the lithium ion batteries which are having it is very it is not good for the environment, and it is also a high cost, and then it takes more space. Okay. And then to avoid this one, we started exploring the TNG based, the sustainable energy harvesting. For that, to get a more power, and which is characteristics which are needed: portability and sustainability and miniaturization and renewable resource. And what is mechanical energy? Usually, there are three kinds of mechanism happens, and the first one is the electromagnetic, and second one is the piezoelectric based, and the third one is triboelectric based. And here we have chosen the triboelectric based, which are having mostly most abundant in the nature, and then it will give a higher output power. And then what are the advantages of this one? Especially the high output power and high output power, and it's low cost and easy of production, and then high efficiency at low frequency and low weight at diverse use in the field. Okay. And then what is the triboelectric nanogenerator? Usually it cannot mechanical energy into the electrical energy. And in this, there what is the triboelectric effect? There are two mechanisms relevant. One is the triboelectrification, and another one is the electrostatic induction. Okay. And when you have a two kinds of material, when you apply between the two materials, if you apply a mechanical force, and it create a surface charge when it attaches, when you detach from the both the material, the voltage difference is created. Then it drives to those electrons into the form of the circuit, complete circuit. And here is the as you can see the video, electrostatic induction process. And this is the basic structure of the triboelectric nanogenerator. Usually, there are two layers will be there. One is the triboelectric layer, material 1 and 2. And usually we'll use a particular spacer, and then two electrodes for the two make it connection and the flow of current. And here is the example of the triboelectric nanogenerator. And the first one is a rubbing of plastic rolled through the hair, and then rubbing of balloon on hair. Usually the static charge, how it will create, as you can in the real time also, when we are in home or somewhere, if you rub it sometime, it will create a static charge. Okay. And why we need to, what kind of material we need to choose? Then these are it should be as a either electropositive material, either it should be electronegative material, which means that either it should be able to donate the electron or able to receive the electron. That kind of nature should be there in the material. This one, the other pair of material should be electropositive, means we have chosen as a silk, I'll tell you later. And then that is electropositive material. And then it should be flexible. And now every device in the people are, most of the people are working on flexible electronics, most of the thing, which is very important now. And then it should be biocompatible, means it is able to integrate with your human body. It should not create any kind of irritation or anything. And here are the silk. Why we have chosen the silk? These are the advantages. It is a biocompatible material, and then it is a flexible material, and you can apply the millipascal of strain in the stress. Then it is able to withstand with that, and it is a biodegradable material. and it is a transparent material. You can use it for optical applications. And then it is a piezoelectric material, and then it is a durable, and it is a electropositive material. Okay, and these are the advantages we have chosen. There are other polymers also there to like piezoelectric material and electropositive material, but it gives because of the silk has a beta sheet content. This beta sheet content, which is it creates in the crystalline nature, that is affecting the more and more to get a higher the power. And here the fabrication techniques and the structural modification to get a higher power. And these are the techniques, different structural modifications, and arc shaped, and spacer shaped, and planar shaped, and zigzag and space. Ultimately, when you are selecting any kind of a structure or anything, to get a higher strain, which it should be withstand, and it can create a more and more surface charge. That's the main reason here we have taken the spacer as a spacer structural modification. And when it comes to surface modification, and we need a higher surface area to create a more surface charge. Okay, and then surface functionalization to create a functional group. So different type of techniques, chemical modification and physical modifications are there to create a functional groups, and it will give a more charges on it if it is an H2 group or COH group based on that. And coming to the composite material, there are different type of material people are using to improve the power to get a more surface charge. And here we have selected the increasing the contact area. For that, what we have done, initially we have developed a thin film based silk based TENG, and then we got a particular output voltage, but it's not enough to use better applications or higher applications. For that, what we have done, we try to create a pores. Then now, if the pores increases, that the surface charge increases. The surface charge increases, the driving current will be more. Okay, for that, what we have done, initially we fabricated by using silicocaines. We prepared the silk solution. The silk solution we put it in a fridge, and for minus 80 degrees to create a solid white kind of thing. And then after that, we lyophilize it for 48 hours to create a porous structure. Okay, and then finally we got the silk porous scaffold. After that, we use it for the TNG. Here we have used one is a copper electrode on the top of it, and the bottom triboelectric nanogenerator is a silk porous scaffold. Okay, and then here the copper acts as a both triboelectric layer, and at the same time as a electrode. And here is the structure and assembly of I2. On top of that, the bottom electrode has a I2O PET, and then top electrode has a copper. And here is the working principle of TENG. Initially, original state, when you apply a mechanical force, how charges will create. And then after that, when you release it, what will happen? When you release it, the voltage difference is created. And after that, when you again it present, always the cycle will happen. When always contact will happen, separation will happen. This continuous contact and separation, it will create the sinusoidal wave, the power, AC power it will generate. And here is the characterization of the silk and porous silk. Initially, we have done the scanning electron microscopy to know the how the pore structure it is there, surface morphology, and then we have done the to know the by using the conformal microscopy, we have done the how the surface it look like, but the surface roughness. This surface roughness is also important to create a more and more surface charge. Okay, and then after that, we confirmed that from same the pore size is 100 to 300 micrometer, and from the conformal microscopy, we confirmed that 98 micrometer RMS value. And then from the FTR, what we have done that to know the usually we used to done for FTR for the to know the functional, what are the functional groups and what are the bonds are there. But here what we want to know that whether beta sheet structure is there or not. Usually the beta sheet structure is a prominently in literature, as per the literature, it is prominently, it is around 15 to 20, 1528 wavelength. It is presence. And then we confirmed that, but from the FTIR, it is a crystalline structure of the silk porous structure, it is present. And after that, what we have done, electrical performance, whether how much power it is able to generate. Here is the initial one is the silk porous scaffold. It shows that it generated almost 420 peak to peak voltage. And when, as you can see in the B, it is a silk thin film. It is almost around 170 volts peak to peak voltage. And then after that, as you apply this contact and separation, when you apply mechanical force and applying and releasing continuous, then you will get a this kind of a graph and a continuous AC signal. Okay, and then what we different load resistance based on the resistance, how it is varying this voltage, and with respect to the current, how at some point, as you can see that the when you apply this load resistance, the voltage got increased and then the current decreases due to the internal resistance of the TNG device. And here is the device reliability, and we have done for a different thickness of the silk thin film for at the same time, and porous steel structure also, and how it is varying the voltage, and we have verified. Then different thickness we have done, or the thickness of the silk scaffold is increasing, then voltage is slowly it is dropping due to the thickness. If it is increasing, the mechanical forces between the two materials are very less, it is able to withstand. And the main problem is it's not able to create a surface charge on the in between the two materials. And after that, we have checked the number of devices, whether it is a constant, it is coming or not. It's identical. Almost there is a negligible change in this. And then after that, different number of weeks in the same device we tested for that, and it is showing the constant voltage generation for 4 weeks. And then here is the different consistent output and stable performance for over the four weeks. And what we have done after generating this output voltage, then we have used it for one of the application. We try to use for the to illuminate the micro LEDs for the 12 micro LEDs we pervert, and we demonstrate the cell powered wearable electronics. It is possible to integrate, especially in the shoe sole and the smart. This is our next continuation work to make it useful regular use and to generate power. And here is the conclusion. We have developed the flexible and the biocompatible silk fibroin TNG fabricated. And then the porous silk, it enhanced the output voltage. And then which we achieved the 420 volts of by using this. And the power is 17 milliwatt. And the power we have power up the for application for 12 LEDs we light illuminated it. And then this is durable and stable and scalable design. It is a promising for the especially in nowadays flexible electronics. Most of the people are using for that to avoid this, especially in IoT devices which are using conventional batteries. To avoid that one, we started exploring this one. It is a sustainable and biocompatible, and at the same time it is a multiple application we can use it. The future scope is the mostly we will integrate this device to the human shoes, and then we'll try to generate more and more put voltage. And yeah, thank you. Yeah, thank you so much.